Okay, well, thank you very much, and I'd like to thank everybody at NRG for giving us the opportunity to talk and share some ideas this morning or this evening, depending on where you are in the world. It's a very interesting time to be involved in nuclear power, where we've got such a dichotomy of interest going on around the world between some markets that are growing very rapidly and others that have taken a different decision regarding nuclear power, so it's interesting. And what I'd like to talk about tonight is the use of real-time engineering simulators and the value they play, not only in the traditional sense as an operator training device, but also from an engineering perspective. And so, you know, how we're providing more value than just from an operator training perspective. I'm sorry that my colleague Steve Friel can't be here, and I'll do my best to fill his very large shoes. Before we get into the details of simulation use, I thought it would be good to give you just a few minutes of background on GSE systems and our role in the market, both from a training and from an engineering perspective, and a little bit of background in case you don't know who GSE is. First of all, we're very happy to be one of the lead sponsors of the Nuclear Training and Simulation Forum for 2013. So GSE applies over 40 years of what we call best-in-class simulation technology to create some new environments for both training and engineering solutions, and really focused on what we're calling the next generation of energy operating professionals. As I said, it's an interesting time across the entire energy spectrum where we've got new capacity coming online. At the same time, in many countries, we have a very aging and workforce ready to retire. So at the same time where we've got demand increasing and the need for new workers, we have a shrinking workforce, which creates an interesting situation and an interesting challenge for the industry to find ways and technologies to help solve that particular need. And that's what we're trying to accomplish here at GSE. A little bit of the history, in case you're not familiar with the name GSE, you might be familiar with some of the other names we've gone by in the past. We trace our history all the way back to 1929 and what we call the dawn of the simulation industry, when perhaps one of the first simulators built for flying aircraft called the Blue Box was created by a gentleman named Ed Link. And we trace our history from Ed Link all the way through the Singer Company, S3 Technologies, and now GSE Systems. And on the bottom of the screen, you'll see, some of the dynamics that have been happening in the marketplace. What's driving the industry, whether it was the first nuclear simulator we built back in the early 1970s. Obviously, the events at Chernobyl and 3 Mile Island had a dramatic effect on the use and value of simulators. And as we moved into the 1990s with computing power increasing, doubling on an annual basis, the ability to bring in more engineering codes has really reshaped the use of simulation, particularly in our market space. And now we're facing things like growing capacity at the same time we have an aging workforce. So leveraging our simulation heritage, we're really focused in 2 areas. One is in training, and a very lofty goal that we have in changing the way the energy industry learns. If we go back and think about how we learn versus how the next generation of workers learns, there's a dramatic difference. And we're using our simulation technology combined with other technologies regarding visualization and other learning content to provide what we hope to be a faster, more engaging, more effective learning environment for the next generation of workers, getting away from the chalk and talk and providing hands-on experiential learning. Of course, the other application, again, because of the ability to start integrating true engineering code into the simulators, we're now using the simulator environment not only for training, but for engineering design, verification, validation. And that's really where the topic of tonight's or today's discussion will head in a minute here. So as I said, as we try to change the way the energy industry learns, it's the application and the underpinning of high-fidelity simulation, but being applied in some new areas, whether it's how to visualize what's happening inside of a reactor, so you paint that correct mental model for the students. In a training environment, you're really trying to help the student picture what's happening in the plant. And if we can use technology to help make sure that not only do they get the picture at the same time, but they get the correct picture, and that helps them understand these complex processes and concepts a lot faster. And we also are using visualization for task-based training, whether it be equipment diagnostics, equipment fundamentals, plant walkthroughs, and things like that. We're very proud that we have a very global reach in our company. As you see across the top, we have over 1,000 installations and 160 customers around the world. Obviously, all of that is not in the nuclear power. We also serve the thermal power industry, the process industries for oil and gas, refining, chemicals, especially chemicals, petrochemicals. And we've got offices around the world in the U.S., Europe, and Asia to support those activities. So jumping into the real meat and why you dialed in here today, I wanted to talk about, start with some of the things we've noticed, I guess, as we've been out of the marketplace working with customers, applying simulation both from an engineering and from a training perspective. Obviously, the introduction of digital instrumentation and control is a key factor in the power industry, more so probably for nuclear than in thermal power, since it's been used in thermal power for many years. As a new plant's designs and life extensions come online, the industry and equally important, the regulators' understanding of these systems is really critical. So the real-time dynamic simulators playing a new role in servicing those challenges of the market. So maybe in order to understand where we are and where we're headed, we take one step back and look at where we came from. So if we look at real-time simulators back in the dawn of that age, back in the 70s, 80s, and even into the early 90s, we fully modeled the plants, but simulation back then truly was as much an art as it was a science. The engineers had to find ways with limited computing power to figure out how to replicate that control room so that the operator could tell no difference between the simulator and the actual plant control room. Often these models were what we call handcrafted. Another word is there was a lot of engineering discretion and personality in the development of some of these models, and they were fine for the purpose back then, which was, again, replicating what's happening in the analog control room or panel control room environment. Obviously, today the situation has changed a little more. We're using a lot more higher fidelity technology. It's pretty much the same scope of supply as far as the level of detail regarding the simulation. But the tools we're using are totally different than they were 10, 15, 20 years ago. We're now introducing true engineering grade models for thermohydraulics and reactor kinetics. We're using GSE, what we call our high definition platform, the first principle models for all the other plant systems. And then obviously the digital control systems and the modern human machine interface provides a lot more, there's a lot more information available to the operator than there was in the past. So how you deal with that information becomes quite important. Some of the other critical issues, particularly for the new plants coming online or being designed right now, obviously we're introducing new technology that's never been tried and tested. The new control systems and information systems are extremely complex and have complex logic and control. The plant is integrating a lot of, I'll say, disparate technologies for the first time. So even though there is a push towards standardization of nuclear plant designs, the AP1000 is a prime example where you still can have a nuclear island designed by one company and the balance of plant conventional island designed by one or more other companies. So integrating all that technology is still a challenge as it was at the dawn of the nuclear age. In coordinating the technology between the providers for the different units, ensuring that the technologies are integrated is a big concern. And obviously getting these plants online, generating power as quickly as possible is squeezing schedules in order to get a better return on investment, and we need to find ways of using technology to help achieve that goal. So what's the role of an engineering simulator? And I'll go into some of these in more detail. One is that we call it a holistic engineering verification validation platform, meaning you can see your entire plant, and oftentimes the simulator may be the first time you see your entire plant operating before construction and commissioning. So it's not a system by system view of your plant, but it's how those systems work together. Obviously, it's well known that they're using simulation for verifying and validating the control system design and implementation. Human factors engineering is another key use for simulators these days. And with new plants, we're talking about new designs, and therefore we need new procedures. So using the simulator to help develop and then ensure that the procedures are going to result in the plant operations that expected. And then at the end of the day, you still have your ANS 3.5 training simulator, but you actually have that available to your team a lot earlier in the construction process. And what we have found is that even to our surprise, the simulator really is on the critical path for a new plant design. The need to have licensed trained operators, the need to have licensed trained instructors to train those operators drives the need for that simulator a lot earlier in the plant design and construction process than I think anybody anticipated a few years back. So if we're going to be using simulators to really test out many aspects of the plant, we also need to ensure that the technology we're using is robust to match that task. So we are using several different, I'll say, industry standard or very well industry recognized technologies. So for the reactor thermal hydraulics, we use a real-time implementation of the Idaho National Lab RELAB 5 3D model. We use the Studsvik Simulate the Neutronics model when we're doing severe accident design or severe accident modeling for containment, spent fuel pool, and those instances. We use EPRI's map code. And then GSE has its own suite of high-fidelity, high-definition tools that we use for the balance of plant, dynamic modeling, logic and control, electrical systems, and human-machine interface. In this bottom area, the key is the models now need to be predictive. We're designing everything based upon engineering information, and we have to come out with the right response. There's no plant data there to try and match and tune your simulator to. The simulator basically has to be able to predict how the plant's going to behave, and the only way to do that is to ensure that the underpinning technology that you're using is going to support that level of detailed information that you need. From an INC design platform, we've come up with something we call Control Sim, which is a platform that integrates the logic and control design tools, the man-machine interface design tools, and a very robust and fully integrated information management system that not only is information management but configuration management system as the plants change. So as we're building our simulator during plant construction, obviously data comes in buckets to us, not all at once, and we have to be able to manage the changing information and do that in a very robust and seamless way for the customers. So the Control Sim environment is also used by some of our customers as they are trying to take more control over design of the plant INC. So the same set of tools that we would use to simulate the plant INC, the customers are using to do that top-level design, developing the base icons, the control logic design, creating the IO list, the AutoCADs, the set point definitions, and basically coming out with a DCS specification. And all the time we're bouncing those designs against the simulator and the dynamic models to ensure that the strategy is going to work and the implementation of the control system is going to result in what they expect. So again, just an idea about the different types of things that we look for. The interaction between safety and non-safety systems, the interaction between control room and non-control room operations, and then again ensuring whether the logic and control has been implemented correctly. And the next slide gives you an idea of the experience we've gained both in nuclear and in thermal power, as we've used simulation to test out DCS systems. And these are the typical types of problems, and it's unfortunately not just one or two that we find. You know, it tends to be hundreds depending on the stage of the project we're in. And you know, whether it's incorrect permissives that would prevent equipment from starting up, you know, incorrect tags, loops not connected. It's a wide variety, oftentimes not big mistakes, and if we can find them on the simulator, they're relatively easy and relatively inexpensive to find. If you're trying to find these during plant commissioning, it's obviously the most expensive time you could be trying to solve these problems. So using the simulator, you know, just makes a lot of sense. From a human factors perspective, there's a lot of different things we've been able to do using the simulator. One is the layout of some of these new control rooms. So whether, again, we're talking going from an analog control room to a fully digital or a hybrid control room, you know, what information do we have in the control room? If we look at some of the new small modular reactors where a single control room may have up to 12 different reactors being operated, you know, the paradigm is shifting. You know, how many reactors can a single operator manage? So using the simulator has helped some of these companies determine what that optimal number is, and more importantly, it will help them convince the regulators that that change in operating philosophy is still going to be safe and effective. But back to the details that we tend to uncover using the simulator from a human factors point of view is where should the information show up? You know, how much information should we have? What's the navigation through what will likely be hundreds of DCS screens? And you know, the density of information, the concern about information overload. In the old days, it was very difficult to change the information provided to the operator within a control room. Now, with the DCS, there's, you know, hundreds of thousands of bits of information that potentially could be presented. So, what is that right information, and how easily can the operator diagnose and resolve a problem? You know, how many clicks does it take to find out what's really going on in your plant? We now have new modern alarm management systems. What's the role of the shift supervisor? You know, what information does he have readily available, and how do we share that information across the entire control room? A big push now for electronic procedures and how we interface with them. And then, as I said before, you know, not only is it getting the operators comfortable with these new designs, but it's also getting the regulators comfortable with these designs. So a few examples of things that we've been doing here in the United States with the U.S. Nuclear Regulatory Commission is developing human-machine interface designs connected to existing simulators so the regulators themselves can get a better appreciation for how these plants will be run and what their role is in regulatory space. And same thing with other aspects of the U.S. NRC, Idaho National Lab. And you know, this is why we feel somewhat qualified in talking about this, and we've been working on a lot of what we'll call first of an engineering simulator projects, whether they be nuclear or non-nuclear. Westinghouse AP1000 and the simulators that we're building with them for the Haiyang and Sanmen plants in China, as well as the Vogtle and Scana plants here in the United States, working with several different small modular reactor design companies, whether it be NuScale, B&W's mPower, the Carey Smart Reactor from Korea, and what used to be the Pebble Bed Modular Reactor out of South Africa before that project was terminated. We're also working in non-nuclear space, and again, bringing the experience that we've gained in the process and in the thermal power industry, you know, adds some value when we're talking about DCS integration, human factors, and using simulation for design V&V, even in the nuclear space. You know, one example is using our simulation technology to help do DCS V&V for the Chinese CPR 1000 design. So we used our simulator to help design the control strategy, the human-machine interface, the automated procedures. As you can see from that third dash, you know, we went through extensive revisions of the DCS in order to come up with the final design that they felt would really work. and again, automated the plant procedures and understood how to do that. Project was really a raving success, and the customer got a lot of value out of it, and we kind of continued taking the next steps with that customer in implementation of simulation for V&V and helping them with their design processes. Some of the success factors, just a little bit of a wrap-up, is, again, using the engineering grade predictive models is key when you're trying to really understand how the plant's going to behave, whether the procedures are going to work, how the operator is going to interface, whether the DCS has been designed and implemented correctly. But it's also important that we look at a different relationship between the vendor and the contractor. Again, in the old days of building a simulator, the customer would give us a truckload of data and we'd go off and design a plant. Now we get that data in an iterative fashion, and we have to do more of a spiral design approach, which means we have to have a lot more coordination with our customer, a lot more flexibility in the design and how we schedule things and how things happen than have ever been required in the past. But we've also noticed it also provides a benefit to our customers in really helping their different engineering departments, whether it be design or instrumentation and control. It almost forces them to work together where in the past they may not have had to, but in order to achieve the objectives of the simulation project, really looking at it as an integrated team approach between GSE and the various engineering organizations really is a real key to that success. And then obviously, our experience in doing full scope simulators across a variety of design platforms gives us the benefit to provide some valuable engineering insight to our customers and to that partnership relationship. So bottom line is, the kind of the value of using the simulator in this aspect. It really comes down to how do you drive risk out of a project, how do you drive cost out of a project by using the simulator to validate, both the plant processes, equipment sizing, things like that, control systems, human-machine interface, and the human factors engineering, plant procedures. And really, the bottom line is the bottom line. Identify and correct design flaws, as early as we can in the design process when it's the least expensive time to try and correct them. So with that, I thank you for your participation and be happy to answer any questions that anybody has.
Yeah, perfect, Gill. Thank you so much for your presentation. We have a question from the Tsinghua University, a research associate. He wants to ask us on how events like Fukushima and Daiichi affected the improvement and development of full scope simulators.
Well, I think it has caused us to rethink some of the operating paradigms. So for example, some of the things that we've seen happening here in the United States, even before regulatory mandate has dictated what will happen, is we're starting to see customers looking at certain plant models, and particularly if their plant simulator had been built many, many years ago, they're looking at more robust, for example, electrical system modeling. So the practice or the theory in past had often been, that we would go without site power for a certain period of time, and your simulator may have to run for 8 hours or 12 hours. Now we're looking at events where you might have to run your simulator 72 hours. And during that process, you have to really understand what the effect is of operating decisions on battery life and electrical buses around the plant, and what decisions you can make to extend the useful life of key equipment. So now we're starting to, have been for the past couple of years, providing much more detailed electrical system modeling down to a much lower level within the plant than was ever required before from purely operator training. More robust containment system models, potentially using MAP not only for the severe accident and beyond design basis scenarios, but also in normal operations. We're starting to see that. The next generation will start more actively modeling spent fuel pools and things. So we see kind of the need to do some basic upgrading of some of the simulators that are out there. Once the regulatory environment here, particularly in the United States, gets a little bit clearer, we will see, the introduction potentially of MAP or MELCOR or other severe accident codes embedded within the full scope simulator. And we actually see probably more interest and activity in that regard outside of the United States than we do with U.S. utilities at the moment.
Perfect. He also wants to know, is a little bit focused about the business, but basically he wants to know if the demand of the full scope simulators around the world is being increased due to these events.
I didn't quite hear what has been increased due to the events?
Basically the demand of full scope simulators around the world.
Well, I mean, the use of full scope simulators has been a well-adopted best practice, for the past, I'm going to say 20 years. Obviously, in the United States after 3 Mile Island and more worldwide after Chernobyl. I think what we're seeing is the understanding that the role plays of the simulator plays differently than just from an operator training perspective. On the one hand, there are certain areas of the world that continue to develop nuclear power quite robustly, whether it be in China and Russia and some other emerging markets, whereas, in Germany, just the opposite has happened so far. So I can't say that the event of Fukushima has increased the demand, because I think that demand has always been there. I think what we're seeing is the potential addition of simulators for customers that were using one simulator to train on 2 units. I think the throughput is increasing, and the fact that we're now using simulators to train more than just operators, but engineers and management and others, the need for more simulator time has forced or has allowed some customers to decide to build a second full scope simulator. So if they've got 2 units that were nearly identical and could use one full scope simulator, they're now looking at that investment of another full scope simulator in order to provide more training throughput.
Well, I think it's clear. We have another question from CMPS Corporation. They want to know a little bit more about the development of full scope simulators for AP1000 in China by GSE, of course.
Well, so I can tell you things that are in the public domain. So I think we announced many years ago that we had signed a cooperative venture with Westinghouse to be their provider of the full scope simulators for the AP1000 plants. And the first 2 projects that we have underway are for the Sanmen and Haiyang plants in China. And I think there's been information out about the fact that the simulators, one has been fully accepted and is used in training, and the other is very near to that. There's a slight difference in the project schedules between those 2 plants, both from a plant construction point of view and from a simulator point of view. And GSE also built a second simulator, again, to help provide more throughput for training for the operators at the Haiyang plant. So the kind of the working relationship with Westinghouse has been very good. They've used the simulator for basically each of the aspects that I just discussed. We started off using the simulator for human factors engineering of the control room, and it's still being used to, again, validate and verify implementation of the control systems. So the GSE scope of supply is the dynamic modeling of the plant models, and the Westinghouse scope of supply is the hardware and the INC system. And so we've been we've been working hand in glove with Westinghouse for many years now and providing these simulators.
Perfect. I think it's also clear. And we have a last question from the Gill University. And, well, basically, it's what is the difference in terms of regulation and restriction to work developing, well, full-scope simulators here in China? And in your opinion, what will be good to be improved in these terms?
Well, I mean, from a simulator standards point of view, I really don't see much of a difference at all. You know, there's a well-adopted, I'll say, minimal standard for nuclear power plant simulator design, which is the ANS 3.5 standard. So most people adopt that. Some request a higher fidelity solution, but that is the minimum. So all the simulators, I think, being built around the world pretty much meet that standard by any of the vendors. I'd hate to say, you know, from a regulatory point of view, you know, what the differences are between the China regulatory environment and the U.S. regulatory environment, just because I'm not an expert in that. But if the colleague with the question would like to stop by and visit us during the conference, we will have some experts there that might have an opinion on that.